Now, based on the properties we have seen, reflexiveness, symmetry, anti-symmetry, and transitivity, we can define two important classes of relations. The first one is equivalence relations, and the definition is given here. A relation R on set A is called an equivalence relation if it has three properties: if it is reflexive, if it is symmetric, and it's transitive. Okay, reflexive, symmetric, and transitive relations on set A is called an equivalence relation. Okay, now when we have an equivalence relation and x and y are related through an equivalence relation, we say that x and y are equivalent. Okay, so this equivalence we sometimes denote with this notation or sometimes with this notation. And for the set of all elements that are equivalent to an element x, we call the equivalence class of x. Okay, so this is a set and it includes all elements that are related to x via this equivalence relation. And this is the notation we are going to use. And sometimes in some textbooks, you can also see this notation when it is not ambiguous, meaning that it will not be confused with the complement operation. You can also use this notation. But to be clear of that, we are going to use this notation in general. Here's an example. Let's define the relation R on set -3 to 3, set of integers from -3 up to 3. The set of ordered pairs such that the absolute values of x and y are equal. Now, obviously, -3 is equivalent to -3, and -3 is also equivalent to 3 via this relation. So the equivalence class of -3 and also the equivalence class of 3 is equal to -3 and 3. Similarly, the equivalence class of -2 and 2 consists of these two elements. The equivalence class of -1 and 1 consists of these two. And the equivalence class of 0 consists of only 0. How do we see this is an equivalence relation? You have to check these three properties. Is it reflexive? Yes, because the absolute value of x clearly is equal to the absolute value of x, so it is reflexive. Is it symmetric? If you have xy, do you have yx? Yes, because if you have xy, that means their absolute values are the same, which means you should also have yx because their absolute values are the same. Is it transitive? Yes, because if the absolute values of x and y are the same and the absolute values of y and z are the same, that means the absolute values of x and z also must be the same. So it has all three properties, which means it's an equivalence relation. Now here you see the equivalence class of -3 and 3 are the same, and it consists of those two elements. So this structure is not a coincidence here, obviously. And here we are going to prove a result based on this observation. We have three statements here, and we will show that they are all equivalent. Let R be an equivalence relation on A. For all xy, the statements x is related to y. The equivalence classes of x and y are the same. And the intersection of the equivalence classes of x and y are not empty. These three statements actually imply each other. So what we have here is something like I biconditional 3, something like that. So we have biconditionals all the way. So this is something like I in biconditional I and I biconditional 3 and 2 biconditional 3. Okay, so essentially what you have here is a set of 6 implications. 1 implies 2, 1 implies 3, 2 implies 1, 2 implies 3, 3 implies 1, 3 implies 2. But it will be sufficient to prove just 3 of them. I'm just going to prove 1 implies 2 and 2 implies 3 and 3 implies 1. When I prove all of these 3, they will entail the remaining 3. So I'm not going to do this, do all 6, I'm just going to do 3. So let me clear all these. The first implication, 1 to 2, that means this implies this. How do I see when x and y are related? Their equivalence classes also must be exactly equal. Now, remember, R is an equivalence relation, so it has three properties. It's reflexive, it's symmetric, and it's transitive. Since it's symmetric, when this is true, x and y are related, then also this also means y and x are also related. So I have xy, I also have yx. Suppose there is an element z in the equivalence class of x. This means x and z are related, which also means z and x are related. And since R is transitive, look, I have xy, I have yx, I have xz, and I have zx. Okay, for instance, take this one and this one. Since R is transitive, you have yx and xz. That means you should also have yz. And from symmetry, you should have zy. This means whenever z is an element in the equivalence class of x, it also must be in the equivalence class of y. This shows that the equivalence class of x is a subset of the equivalence class of y. Now, I can do the exact same thing in the other way. So if I assume z is an element in the equivalence class of y, from this, I can arrive at the conclusion that the equivalence class of y is a subset of the equivalence class of x, and these two together will give me that they are the same sets, they are equal sets. Okay, so this one implies this. Let's look at the second part. 2 implies 3. Now let's see what this means. The equivalence classes of x and y are equal. Does this imply that the intersection of the equivalence classes of x and y is non-empty? Now we know that R is an equivalence relation, which means that it's reflexive, which means in the equivalence class of x, if there is nothing, there is x. Okay, this means x is related to itself, which means in the equivalence class of x, there must be at least one element which is x itself, which means x, the equivalence class of x is not empty. Now, these two sets are equal, and when you take their intersection, now remember, if A and B are equal, or let me just write this, A intersection with itself is just itself for any set. So these are sets, and I know that they are equal sets, and when I take the intersection, this should be equal to any one of them. And I know that there is at least one element, x, which makes this a non-empty set. So yes, this implies this. Okay, let's do the third one. Does 3 imply 1? Okay, the equivalence class of x and y, when you take the intersection, it's not empty. That means there is at least one common element. Okay, the intersection is not empty. That means there exists a z value such that z is both in this set and in this set, which means x is related to z and y is related to z. R is symmetric because it's an equivalence relation, which means we have xz and also zx, and we have yz and at the same time zy. Okay, and I also know that it's a transitive relation. Now let's look at here. I have xz and I also have zy together. Due to transitivity, I should have xy. So this here, yes, implies this. Therefore, I have proven that these 3 statements are equivalent when R is an equivalence relation. If X and Y are related, then their equivalence classes are exactly the same set. And when X and Y are related, then the intersection of their equivalence classes cannot be empty. Or it's the other way around. If the equivalence class of X and the equivalence class of Y have at least one common element, then you automatically know that X and Y should be related, and these two equivalence classes are exactly the same sets. Okay? Now, from this, it follows that when the equivalence classes of two elements, X and Y, are not the same, this means they have to be entirely disjoint. Okay? They cannot have any common elements if X and Y are not related. Because we have shown that if they have at least one common element, then they must be entirely the same sets. If that is not the case, then they cannot have one single common element. So the intersection should be empty. Also, since R is reflexive, when I unite all the equivalence classes, I will have all the elements inside A, right? Because every element is related to itself, so every element is in at least one of those equivalence classes. So when I unite them, I will have the entire set. Now, based on these, we see that equivalence classes of a relation R on set A constitute a partition of set A. What's a partition? This is the definition. A1, A2, up to AN, n sets here. They form a partition of set A if, first of all, when you unite them, you get the set A. Nothing is left out. And number two, they are all disjoint, no common elements. So something like this. If this is your set A, this is a partition, okay? All elements, sorry, all sets, when you unite them, you get set A, and there are no common elements. This is what we call a partition, and from the theorem that we have just proven, we see that equivalence classes of an equivalence relation on set A constitute a partition on set A.